Okay, hello there. In this video, I'll be solving for the, I've solved this before, so I'm just going to show you what I've done. So, I'll be solving the um, wave function, the psi, given these quantum numbers. So, as you can see, the emphasis there on the 7i, sorry for that blur. These quantum numbers are assigned to us by our professor individually. So I got these quantum numbers. So given the principal quantum number of 7 and azimuthal quantum number is 6, so it represents the 7i orbital. In particular, more specific, we'll have the ML, the orbital angular momentum, quantum number of positive and negative 5, and we'll also account the spin quantum number of positive 1/2. So to start off, for the psi, we know that it comprises the radial function and the spherical harmonic functions. So the spherical harmonic functions are composed of the theta, the capital theta, you see with that h, and with the phi function. So the theta function accounts for the L and ML quantum numbers, while the phi accounts for the ML quantum number. Then we'll also account, lastly, the radial function, which accounts for the N and L quantum numbers. So to start off, we'll solve first for the R. So the R is equivalent to this formula right there, the bottom. After knowing the formula, we're going to substitute the values of L and N. So given the N, which is 7, and L is equal to 6, so N minus L minus 1, there in the summation, will give you 0. So substituting 0 in the J, so we'll have the B0 R raised to 0, which is R, wherein R raised to 0 is equal to 1. Well, so the final equation for the radial function is B0 R raised to 6 a negative 7R over 7A. However, this is not yet done. We need to normalize this. So by normalizing, we account the complex conjugate R and the R itself times R squared, and integrating it with limits of 0 and infinity will be equal to 1. So solving for that, so there, you substituted the R value. So remember that the complex conjugate and the non-complex conjugate, should I say, is the same, pretty much the same. So there, using the one above the equation. Then isolating the B naught, since it's a constant, so multiplying the R raised to 6 times R raised to 6 times R squared will give you R raised to 14. Yeah. Then further simplification will give E negative 2ZR over 7A. Then this can be integrated using integration table. So there's the formula right there. X raised to n multiplied by e raised to negative ax, integrating with limits, is equivalent to n factorial over a raised to n plus 1. Wherein your a here in the former equation is 2z over 7a. Now, after getting the integral formula, we now substitute. So we know that n is 14, so 1 is equal to b0 squared times 14 factorial over a. So our a is 2z over 7a. So 2z over 7a raised to 15. Afterwards, simplification of the equation. Okay, simplification. Then, multiplying all the constants, so the 14 factorial, the 7 raised to 15, and the 2 raised to 15. So that will be equal to 1.26 times 10 raised to 19. Then, further simplification again. So there, you have the b sub 0. So after getting the b sub 0, the square root, so you have it right there. So 2.81 times 10 to the negative 10 times z over a raised to 15 halves. Then substituting the b sub 0 in the equation of the radial function, will have this formula right there. So the final radial function for this orbital, so 2.81 times 10 raised to negative 10 multiplied by z over a quantity raised to 15 halves times r raised to 6 times e negative zr over 7a. So we now have solved the radial function. So next we're going to solve for the theta function. So remember, the theta function accounts for the azimuthal and orbital angular quantum numbers. So here's the formula. So for theta, so the maximum of the summation for the aj cosine theta term is 1. So it follows there L minus M. So 6 minus 5 is equal to 1. So inputting this, so we'll have sine theta raised to 5 times cosine theta raised to 1 multiplied by a coefficient a sub 1. So simplifying that, we'll have a1 multiplied by sine theta raised to 5 times cosine theta. Now we're going to solve a1. So how do we do that? Just like in radial function, we're going to normalize. So normalization, so the same formula with the radial function, but this time we're going to use the theta function, the theta eigenfunction should I say, with limits of 0 to pi, then multiplied by sine theta is also equal to 1. Okay, the same procedure, so we go the same complex conjugate and the actual eigenfunction. So there, multiplying these two eigenfunctions will have this. So why did I separate a single sine theta there? So we'll see. Okay, next. The sine 10 theta can be trigonometrically converted to 1 minus cosine squared theta raised to 5. So as we all know, the sine squared theta is equivalent to 1 minus cosine squared theta. So here's the equation rather. So there. And as you can see, I converted the theta in terms of cosine theta. So I changed the integral. So the tendency is that the integral will be negative. So isolating the negative sign, will have the negative a1 squared. So after that, so we're going to apply square of a binomial for each of the two 1 minus cosine squared theta equations. So squaring that will give you 1 minus 2 cosine squared theta plus cosine raised to 4 theta. Then repeating that for the next two. Then distributing the cosine squared theta. So in a single 1 minus cosine squared theta will give you cosine squared theta minus cosine fourth theta. Then the derivative with the integral with respect to cosine theta is equal to 1. Then next, so we can combine the two previously squared of a binomial terms. So that will be squared. So the 1 minus 2 cosine squared theta plus cosine raised to 4 theta there, times the distributed 1 minus cosine squared theta. So that cosine squared theta minus cosine raised to 4 theta d cosine theta is equal to 1. So the trinomial term is in squares, so that can be algebraically converted into a multinomial. So there, that's the formula. So x squared plus y squared plus z squared plus 2xy, 2xz, and 2yz. Okay. Applying that will give you this. So the square will be 1 plus 4 cosine 4 theta plus cosine 8 theta, and so on and so forth. I'll just going to proceed with the scrolling of the video. Okay. Then inputting this, so right there. So what I just did is I incorporated the converted square of a trinomial and distributing the cosine squared theta minus cosine 4 theta here. So next thing is that we're going to combine the like terms. So combining the like terms will give you this. So, sorry for that. I'll just read it. So cosine squared theta minus 5 cosine 4 theta plus 10 cosine 6 theta minus 10 cosine 8 theta plus 5 cosine 10 theta minus cosine raised to 12 theta times d cosine theta equals 1. So again, simplifying. So here's the previous equation in the previous paper. So there. So we can now actually distribute the integral and apply this formula. So x raised to n, the integral of this is x raised to n plus 1 over n plus 1. So in this case, our x is the theta, while the n will be the exponents. So applying that, so we'll have this. Okay, so after integrating all of the terms, so we're going to set the limits from 0 to pi, since it's a theta function. So cosine theta and cosine raised to 0 are negative 1 and 1 respectively, provided that our n is an odd number. So as you can see, all of our exponents here are odd numbers. So we can say that everything, incorporating the limit, so we'll have negative 1 minus 1 on all terms. So right there. Now, distributing and simplifying the numerical coefficients, so we'll have this. Then simplifying it, so we'll have 512 over 9009 times a1 squared is equal to 1. Then solving for the a1, so we'll have square root of 9009 over 512. Then incorporating again a1 in the theta eigenfunction, so we'll have this. So this is our final theta function. So square root of 9009 over 512 times sine theta raised to 5th multiplied by cosine theta. Okay, so we've done the radial function and the theta function. So next function we're going to do is the phi function. So this is a simple formula, so that's just 1 over square root of 2 pi multiplied by e raised to positive or negative mi times phi. So in this case, in what I've been assigned, so my m is 5. So incorporating that, so we'll just replace the m with the 5. So for positive 5, we'll have positive 5i phi. For negative 5, we'll have negative 5i phi. And finally, incorporating the three eigenfunctions together for the psi, so we'll have this. 2.81 times 10 raised to negative 10, z over a, 15 halves, r raised to 6 times e negative z r over 7/8 times square root of 9009 over 512 sine raised to 5 theta cosine theta multiplied by 1 over square root of 2 theta e raised to positive negative 5i phi. So sorry for that wind. Okay. After that, so we know that the phi function, in particular the e raised to im phi, is a complex function. So in order to simplify it, so we need to linearly combine the two wave functions. So there, so what I just did, so you've probably noticed that the numerical coefficients are combined together. So if they're combined together, we'll have 1.18 times 10 raised to negative 9. So here it is. So applying linear combination, so to account for the complex wave functions of these. So we'll just simply add the two wave functions. So there. So after getting the formula, so we normalize again. Should I normalize? We get the Kronecker delta. So multiplying the complex conjugate of the linearly combined wave functions and the real wave functions, real wave function rather, so equals 1. So applying the psi prime, so just like in the previous equation, so simplification, then distribution, so 7, 6, positive 5. So we just applied FOIL here, so I'm just gonna scroll. Okay, next, after that, so we get the numerical value for the Kronecker delta. So it's either 0 or 1, so the value for the Kronecker delta. If the two terms are equal, so it will be equal to 1. If not, it will be equal to 0. So here it is. So why did we inputted a variable n, so to account for the Kronecker delta, so to account for the linear combination of the two wave functions. Okay, so simplifying that, so 1 plus 0 plus 0 plus 1. So it came from the previous, this equation, the bottom. So two of them have the same terms while two of them have not. I do not have the same terms, so that's why you have 2 zeros and 2 1s. So solving for n, so we get 1 over square root of 2. Then incorporating the n to this linearly combined wave function. So there you go. Then substituting the values of the wave functions, so we'll have this. So what we just did is that we just incorporated the linearly combined, so we accounted for the linear combination of the two wave functions. So simplifying, so there we have Okay, so after getting this, so we can simplify this, the e raised to 5i phi plus e raised to negative 5i phi. So what we do is that we apply this, the Euler's relation. So it is equal to e raised to positive negative I phi. So it is equal to cosine phi plus I sine phi. So incorporating that formula in the two terms, so e raised to 5i phi is equal to cosine 5 phi plus I sine 5 phi. So for the negative term, negative form, so we just change the sign, so it's negative I sine 5 phi. So adding that incorporated Euler's relation, so there, we just added the two terms, the two terms. Sorry for that. So we'll get 2 cosine 5 phi. After that, so we have this, the final psi prime. So there you go. So we just replace the e raised to I phi terms into 2 cosine 5 phi. So there again for the last time. But there's one thing that we haven't accounted yet. So we haven't accounted the spin quantum number positive 1/2. Well, that's just going to be easy because for accounting that, so we'll have this. So we just insert a term, so it's either alpha or beta. So since the one that I'm assigned is positive 1/2, so for that spin, so we're just going to add the term alpha, or multiply, should I say. So there. So this is the final answer for the 7i orbital. Given the quantum numbers n equals 7, l equals 6, ml is equal to positive or negative 5, and spin equals positive 1/2. So there. We just added the alpha term right there. The same. Okay, that's all. So thank you for watching. Sorry for that shaking.